Hi everyone, so today we're going to be splitting up today's lessons into two parts just so we can get a better understanding of what IMFs are. So we're going to start off with part one right now. And so when we look at IMFs, or intermolecular forces, this is the attraction that is found between the molecules. And they're really not as strong as intramolecular forces, but they are still strong enough that they have enough control of the physical properties where the boiling and melting points are going to be impacted, as well as vapor pressures and viscosities. So whenever we look at intermolecular forces, they are also referred to as van der Waals forces. So van der Waals forces are IMFs. There are a few of them. The few that we're going to be looking at are hydrogen bonding, dipole-dipole interactions, and London dispersion forces. Hydrogen is seen as the strongest and London is seen as the weakest, and that's going to be really important going forward. So whenever we look at IMFs, we can look at their states of matter as well as kinetic energy. So when we look at the states of matter, this depends on the balance between the kinetic energy, so the way that those molecules are moving and how fast they're moving, as well as their intermolecular forces. So when we look at that kinetic energy, this depends on the temperatures. That's going to keep the molecules and particles moving as well as apart from one another. And then those intermolecular forces are going to pull them together. So when we look at a solid, liquid, and gas, obviously solids, you can see here from this diagram that solids are going to be very close together because they have strong IMFs. But gases, on the other hand, are seen as quite weak IMFs because their particles are more farther apart, they're spaced out. So if we were to look at a summary of our intermolecular forces between solids, liquids, and gases, solids, they have the strongest, liquids is next, and then gas is last. When we look at melting point, this is also something that impacts our particles and our IMFs overall. So when we look at the temperature where the solid changes state into a liquid, we know that heat has to be added. And the more heat we have, then that means the particles are going to be moving faster, they're going to vibrate more, and it's going to be much, much quicker than if we have less heat added. So when we have enough heat, the molecules are going to have enough energy to move away from other molecules, and they are now overcoming those IMFs that we have seen in our solids. So the solid begins to melt and it becomes a liquid. So when we look at solids becoming a liquid, we have to add heat, and we have to have a certain amount of energy in order for those IMFs to break from solid state to a liquid. And then once that force is broken, then the substance can now go from that solid to a liquid. And then if you continue adding more and more heat, then enough energy is going to be there, and it's going to overcome the IMFs again, and it's going to go from a liquid to a gas phase, and that's known as boiling point. So an example here, we have NaCl. It's a solid at room temperature, and that's when the molecules are going to be bonding via intermolecular forces. And once they begin to melt at a specific temperature, that means we have enough energy in order to overcome those forces, and then it can start going into a liquid phase. So here you can see the example of the physical property of NaCl, where it has a very high melting point. So they're held together by IMFs, but once heat is added, then we are able to break them apart. Next is pressure and states of matter. So if we increase the pressure on gas, then the gas molecules are forced to be close together, and this strengthens those IMFs when we look at them between gas particles. So for example, propane is a gas at room temperature, and if that means that if we increase our pressure of gas, then we have to have a lot of pressure to change that state. So if we want to go from a gas to a liquid, we're going to have to increase that pressure by a lot. So here is a great chart that we can reference even from like grade 8 when we took a look at this. So if we want to go from a solid to a liquid, we have to melt it, and then vice versa. We have to freeze it. And then we go from solid to gas or gas to liquid, vice versa. We have different processes that take place. So remember that we are looking at different intermolecular forces, and they're also known as van der Waals forces. And our first one that we're going to be looking at in just general, get a better understanding, is our ion-dipole interaction. And this is a type of force that does occur. Even though it's on that list, it's still a force that does occur. And when we look at ion-dipole interactions, they are an important force that we see within solutions. And when we look at the strength of the forces that are coming about, it's only possible because the ionic substances dissolve in polar solvents. So just in general, understand that when we look at ion-dipole or dipole-dipole, what happens is that the negatives are attracted to the positives and vice versa. If we have like charges, they're going to repel one another. So ion-dipole is very similar to dipole-dipole. Just the fact that if we have cations or anions, they're going to have a dipole moment, which means that they're going to be attracted to their opposites. So dipole-dipole, same sort of thing, but we have polar molecules that are attracted to one another. We have our partially positive end is going to attract our partially negative end and vice versa. And you can see here these solid red lines mean that they are being attracted to one another because they're opposite charges. The blue lines, they're repelling one another because they are similar charges. So throughout, we have dipole-dipole moments that do occur. These are some examples of dipole-dipole interactions that do take place. And if we have a more polar molecule, and we can determine something is more polar, the higher the boiling point and freezing point it will be in order to break that bond. So that is a dipole-dipole interaction. The next is hydrogen bonding. So we can look at all these different examples. We have this blue line here, which is our non-polar series that is going on. And it's following the trend that we expect it to. It's going from period 5, 4, and it's going in a kind of straight line. When we look at the other polar series, what happens is that we start going in the same sort of trend, but then it shoots up. And on all three of those. And we can look at them and be like, why do we think that is? And that is because of hydrogen bonding. So when we look at hydrogen bonding, the dipole-dipole interactions experienced when hydrogen is bonded to either nitrogen, oxygen, or fluorine is actually very, very strong. So all these are hydrogen that is bonded to either nitrogen, fluorine, or oxygen. And when we look at hydrogen bonding, it can only happen within those compounds. So these are known as hydrogen bonds. And when we look at them, it is caused from very high electronegativity within our nitrogen, oxygen, and fluorine. And any molecules with those hydrogen bonds will have a high boiling point. So it has to be with nitrogen, oxygen, and fluorine. So this is known as hydrogen bonding. And when we discussed at the very, very beginning, and we looked at what is going to be the strongest, what is going to be considered the weakest, whatnot, hydrogen bonding was seen to be the strongest, and that is because of its electronegativity. And then last is London dispersion forces, which is our weakest. And so when we look at electrons in its 1s orbital, and we can look at helium here, we see that what happens is that they actually repel each other, and so they tend to be far away from one another. But it does actually happen that sometimes they occasionally wind up on the same side as the atom as shown here. They're on the same side. So what happens when they move to the same side, the helium atom is polar, and it has an excess of electrons on the left side and a shortage of electrons on the right side because of where the electrons move. If another helium does come by, then they would have a dipole induced in it because of the electronegativity that changes and all electrons are moved to the other side. And so the electrons on the left side of the helium are now going to repel the electrons in that other cloud of helium on the other atom. So you can see here that the electrons on the left side of helium-2, that they were together, they actually repel the electrons in this cloud. So these electrons in the cloud of helium atom 1 move away, and it creates a bond with that nucleus instead. And that is known as a London force of attraction. And it's an instantaneous dipole as well as an induced dipole. And so what happens here is that you can see the attraction going on. It moves the electrons from the other helium away, and it creates a bond moment with the nucleus of that helium atom. And these forces are going to be seen in all molecules, whether they're going to be polar or nonpolar. So we do have some factors that can affect our London forces. And so the strength of London forces tends to increase with increased molecular weight. So as we get larger, then the strength also increases. And if we ever look at large atoms, they have these large electron clouds, which makes it quite easier to polarize in any situation. So, little summary. So dipole forces, we have molecular molecules that have higher intermolecular forces than non-molecules. If we look at its boiling and melting points of these polar molecules, it's going to be seen as higher than those non-polar molecules if they have a similar mass. And the forces are only effective when molecules are within close proximity of one another. And if we have a large dipole moment, the more polar the molecule is going to be, and the larger the strength of the dipole, which means the larger the melting and boiling points will be. So there's also some factors that can affect the strength of London forces. One is the size of the molecule, which is the molecular mass. So if it gets bigger, the London forces get stronger. And also because of that, the number of electrons increase, and they move quite far away from the nucleus. So that means any large molecules, the polarizability of the molecule, and that means our very strong London forces, even though they're considered to be weak. So here's an image here. The larger the molecule, the more electrons, the stronger the attraction that's going to be, because it's really pulling on the other atom that's close by. Okay, so we're going to pause here. Okay, so that was a little summary of everything. Just make sure that you do understand those different examples